Okay, we are going to take a look at molecular shapes a little bit today, and we're going to use something called valence shell electron pair repulsion. Now we know a valence shell, or the outer shell, the outer layer of electrons, and electron pair is just exactly what it says. And since electron pairs are negatively charged, two electron pairs are going to repel each other, hence the term valence shell electron pair repulsion. And let's start with this very simple substance. Uh, VEH2. Now, I know all the Lewis structures we've talked about so far have said, okay, we need to have a full octet for everything. Well, beryllium hydride is not going to work out very well for us giving a full outer shell because beryllium only has two pairs of electrons in its outer shell. It only has four total. So altogether between beryllium and hydrogen, we don't even have a full octet of electrons. But beryllium can be very stable with just two pairs of bonding electrons. And I can represent this by a simple Lewis structure. Okay, now it doesn't meet the octet rule. As a matter of fact, a lot of what we're going to be doing today is looking at exceptions to the octet rule. Now, in this particular case, I've got two electron pairs. They're going to repel each other. They're going to be as far away from each other as possible. In this particular case, this is a straight line, and I can see the angle between the hydrogen beryllium bond here and the beryllium hydrogen bond there is 180 degrees. Now, even more than that, I can look at the type of hybrid orbitals. On the beryllium, I only have two electrons. So normally I would look at the S and the 2s and the 2p electrons, but I've only got two electrons there total. So in the formation of two hybrid orbitals, there's going to be an s and a p. So if I have two regions of electron density, I have sp hybrid orbitals, okay? 1, 2, sp. If I think of these as having an exponent of 1 each, I have 2. I'm going to add up to 2 for my hybrid orbitals. And sp is associated with this type of molecular shape, which we call linear. Okay, easy enough. Well, let's continue on, and let's look at a couple other exceptions to the octet rule. Let's start with one that's really simple, and that is ALH3. Now again, aluminum is not going to end up with a full octet here. I'm going to have an aluminum and it is going to form a substance, aluminum hydride, that is going to have three regions of electron density. So let's go through that. 3. So I'm going to have an S and two P's, sp2. That is 1, 2, 3, 1, 2, 3. Easy as 1, 2, 3, right? Now, this is going to be a little bit trickier here because when I start looking for the shape, if I want these three pairs of electrons to be far apart from each other, I get 120 degrees. And I know you're thinking, why? Because that's the shape we get. Why? Okay. We don't call it the Y shape. We call it a trigonal plane. Okay, simple enough so far. I have my SP, I have my SP2, and SP2 is trigonal planar. Let's move on to one that we've already worked with a little bit, and that is methane, which is CH4. When I draw my Lewis structure, it looks like I am going to have these electron pairs repelling each other and giving me a 90-degree angle, but that's not right. That would be a two-dimensional structure. In 3 dimensions, we can get them farther apart from that. And we're going to call this shape a tetrahedral. And this bond angle is actually going to be 109.5 degrees. Okay. And in order to show this, sometimes we're going to draw a wedge and a dashed line So the dashed line shows that this goes back in behind the board. A wedge shows it comes out of the board. So I have the ability to show a little bit a three-dimensional structure here. This particular one we call a tetrahedral structure. And this one actually does meet the octet rule. And I've got 1, 2, 3, 4 regions of S electron density. That's going to be sp3. Simple enough so far, right? Well, let's go a little further. Let's look at PCl5. And remember the calculations we were doing to be able to determine how many bonds we're going to have? Well, in PCl5, let's go ahead and do those calculations. I've got 5 and 1 are 6 atoms, right? 6 times 8 is 48 needed. Now, each chlorine has 7, so 7 times 5 is 35, plus the phosphorus, which gives us 40. That's 8 shared. Now, I have 6 atoms. I cannot put 6 atoms together with 4 bonds. What this tells me is that this particular structure cannot follow the octet rule. So if you get an answer that doesn't make sense, the octet rule does not work here. Okay, so let's take a look at what does work. Now, in the case of phosphorus, we are going to end up with d orbitals involved. And I really should put the valence electrons here. Because that one number that I came up with, the total number of valence electrons, 40, I need to be showing 40 electrons. Now this one is a little bit tougher, okay? It is going to show a little bit of a structural difference. So there are going to be 3 of them that are going to be in a trigonal pyramid, and above and below that in the third dimensions, I'm going to have linear ones. So we call this a trigonal bipyramid. Or to make an adjective out of it, trigonal bipyramidal, okay? Notice linear, that's an adjective. Trigonal planar, tetrahedral, trigonal bipyramidal. And when I do the hybrid orbitals, I'm going to have an S and 3 P's, but I've run out of P orbitals. So my next one has to be a D orbital, or more properly, sp3d. And this is a trigonal bipyramidal. Now, I'm going to try to show this. Okay, so let me show you the 3 that are in the trigonal plane. Okay, a little bit. So we're going to show those are in the 3 trigonal planars. Let's say, assume that's in the board that we have right here. And then I'm going to have 1 above and 1 below. And that's very simply how it's going to be. This is a trigonal bipyramidal. I have actually, this bond angle is 120 degrees. This bond angle is 90 degrees. And I also have a 180-degree bond angle. Now, we can keep going. Sulfur hexafluoride has some interesting properties. I know you heard of helium making your voice sound high. Sulfur hexafluoride will make your voice sound low, but don't mess with it. You can end up dying by messing with it. So if I have SF6, I'm not even going to go through the calculation. Well, yes, I will. So I've got 7 times 8. I have 56 needed, and 6 times 7 is 42, and 6 is 48 present. That again is going to be 8 shared, which is not going to work at all. But I do have this number, which is going to be important, the number of valence electrons I need to show. So I'm going to have see if I can draw my wedge here. I have an octahedral shape. And all of these are going to be 90 degrees, or the one opposite is going to be 180 degrees. We call this octahedral. All right, works out pretty simple, okay? What about if I have a multiple bond involved in it, okay? Let's go back to one we looked at earlier. CH2O. Now, I've already shown you how to work with this. However, let's go ahead and redraw our Lewis structure here. In this case, I have a double bond. Now, this double bond is going to count as one region of electron density. Or very simply, I could say I have a sigma and a pi bond here. Now, I'm not saying the right bond is a sigma and the left bond is a pi, because remember, the sigma bond is directly between the two atoms, and the pi bond is that double overlap that goes around. But I am saying that we only need to worry about the sigma bonds here, okay? So I've got a sigma bond here. All of these are sigma bonds, 3 sigma bonds, okay? If I count the 3 sigma bonds, I get sp2 hybrid orbitals, which also goes with our trigonal planar, okay? So if I have a double or triple bond, I only count the sigma bond when I'm determining the areas of electron density. But there's more. What about lone pairs? Okay, so let's take a look at the ammonia molecule, NH3. Now, when I draw this, I'm going to get an N. We'll put the double bond here. I have 4 regions of electron density. And those 4 regions of electron density are going to give me an sp3 hybrid orbitals. I've got 3 sigma bonds on a lone pair. And the electron pairs are going to be in a tetrahedral shape. But when I look at the molecular shape, there's no bond involved here. Okay, so the electron pairs are going to be in a tetrahedron, but these 3 are going to be in the bottom part of a tetrahedron that we call trigonal. Pyramidal. This is going to be a trigonal pyramidal arrangement here, not a trigonal planar. Notice the difference between trigonal planar and trigonal pyramidal. Trigonal planar was a sp2, trigonal pyramidal is an sp3, and I've got 1 lone pair here. Okay, so lone pairs are going to give us a little bit different of a situation. They are going to contribute to the electron arrangements in an atom, but we don't count them when we're determining the shape of the atoms. Okay, so this is our VSEPR theory. It's a very simple theory. It's very useful and can help us to determine the shapes of molecules.